So, just before we start, a short word about one of the organizers, the MUSE project. For those who are not familiar with this project, so GeoArrow is a co-funded initiative of EuroGeo Service of the European Geological Survey Organizations inside the European AeroNet program. We started in July 2018, and most GeoArrow projects like MUSE, one of them, will end in autumn this year. So we were addressing management of shallow geothermal energy use in European urban areas with a special focus on the work of geological survey organizations. So in MUSE, we were looking at 14 different urban areas in Europe. You can see this on the map, but not so much from a technological point of view, but also from the point of view of data assessment, mapping, information system, which in turn provide the basis for decision-making procedures by authorities or city councils. So we are very much connected in the work of what we do as survey organizations, collecting data and using this data for licensing, for decision-making procedures. This also includes energy planning. So today, this webinar is focusing on shallow geothermal resource mapping. So with the term resource, I also include limitations of use, so meaning possible conflicts. And we look at two different, let's say, spatial details. The Geocond project provided pan-European maps, so at a very large scale, which is also very important for policymakers, interest groups, and so on. And in MUSE, we just looked at a very detailed scale. So we don't have any pan-European maps. So we're dealing with the typical problems of data assessment and the use of geodata in densely settled urban environments. And so in this manner, these two projects, they complete each other because we are looking at both ends of the scale, let's say it like this. And I'm very happy that we have this joint webinar today. And we will start having a look on the large scale mapping from the Geocond project point of view. So Burkhard Sander and Adela Ramos Escudero will present the findings of Geocond and have a special look on the shallow geothermal resource maps created. In the second part of our presentations, we will take a look at Austria. So we will, my colleague Martin Fuchsluger and Cornelia Steiner will present a national project. It's called GEL-SEP, which stands for Spatial Energy Planning. Although it was a national project, a lot of the knowledge we developed was linked to the MUSE project and used in the MUSE project. And we will look at a specific problem and a specific solution when it comes to the, let's say, large-scale application of shallow geothermal in borehole heat exchanger fields based on the G-function method and how it can interact with building heat demands. So this is a specific problem because most mapping approaches are used in the past. We're looking at single building use at, let's say, up to 3 or 4 borehole heat exchangers, but more or less acting as a small BHE field or as a single use. And we would like to look at more integrative point of view. Yeah, at the end, we will have a Q&A round and a joint discussion, which I'm looking very much forward to it. But I don't want to waste too much of your time for the introduction, and I would like to now come to our first talk, and I invite Burkhard and Adela to present their outcomes of the Geocond project. So I guess, Burkhard, you start, and the floor is yours. Burkhard, you're muted, just in case you already started.
Okay, you should hear me now, yeah.
Yeah, so, now it works perfect.
It didn't unmute while I at the same time was getting the slides up. Anyway, hello to everybody. Nice to at least have you again virtually. Even all our let's say, intended activities coming over from 2019 had to be cancelled. So it's nice to have one possibility to speak to some of you again. One word to Geocond and the maps. Actually, the most part of this mapping activity was post Geocond and outside Geocond, done at the University of Cartagena. So Geocond started that somehow, and then it got its own life, and that is what Adela will explain later on. And we are not only looking at European, we are also going into a regional detail later on. I'll start with a few words about Geocond. Geocond finished in February this year, so that was almost 4 years of work. The main intention was to improve the efficiency of borehole heat exchanger systems with new materials. So it was a basic research activity looking into the material sciences, and it was a very interesting experience seeing people from the material science struggling with understanding what geothermal is and the other way around. So the main achievements we had were are pipes with a thermal conductivity close to 1 watt per meter Kelvin, Grout with almost 3 watt per meter Kelvin, and with some other nice properties also. Grout with dispersed PCM for improved heat storage capacity, short-term heat storage capacity for UTES systems, and pipes of low thermal conductivity as inner pipes in coaxial or multi-pipe geometries. Oops, sorry, that way. The other. The basic workflow in the project was to first do some research and simulation to determine sensible target properties. This is where the mapping came into the Geocond project, for mapping for thermal conductivities, for instance. No. Okay, no, that was a bit too slow, my computer now. The laboratory research started then working on the agents that are required to obtain the desired properties. Furthermore, research and development followed to create suitable materials, including these agents, and test these materials in the lab. It's rather slow, so I'm not sure what you see now. Okay. The production of materials for borehole heat exchangers up to 15 meters was the next step. For lab testing in a sandbox, that's about a meter or so, done in Stockholm at RISE, and field testing down to 12, 14 meters in a test facility at the University of Valencia. And finally, for these for the materials that had the let's say the highest degree of development yet and of marketability, to upscale the production to real life amounts, to those that are required for borehole heat exchangers for up to 100 meter. And we tested those in real life conditions, both in Germany and in Sweden. So you see here the final, the W heat exchanger and bags with grout for practical use. Still, it is in a test environment, or let's say in a R&D environment. It's not on the market and not very close to the market, let's say. We tested the full-size borehole heat exchangers, for instance, with thermal response tests, and could verify in the large scale still reduction of the borehole thermal resistance by more than 20%. Well, lab was a bit better, but that's the difference between the, let's say, small scale in the laboratory and the real full scale under industrial conditions. For the, well, to define where we wanted to go, we had some basic assumption, which was then also verified with simulations and what I had verified quite some time ago already in earlier programs, projects. The point is that for the optimum borehole heat exchanger performance, the thermal conductivity of the grout does not need to be much higher than that of the surrounding ground. And the pipe thermal conductivity does not need to be much more than 1 watt per meter Kelvin. So these are maps or graphs here from the Enerstock conference. And I'm waiting now. You see, that's the regions where we want to go. If you're increasing the thermal conductivity of the pipes, as in the left or in the right, the grout conductivity, the additional reduction in thermal borehole resistance is less and less. So there is some value that is, let's say, practically viable. This was calculated with ground thermal conductivity of 2.5 watt per meter Kelvin at that time. If the ground thermal conductivity is a bit higher, the value in the right graph will also be slightly higher, but that's what we wanted to find out. Where is the main or the most important thermal conductivity of the ground that we need to target our materials to? So what we did is to look at some maps, not only for thermal conductivity, but a few other indicators like something like drillability. That's also in more extensive done in Project Geo for Civic. Some trying to find something about permeability, etc. The workflow was the following, and Adela will cover that later on in more detail. Geological maps for lithology were created based on the active databases, and we defined 14 main lithological groups to work with from the total of about 500 in the active data. The translation made of this lithology into thermal conductivity using the VDI 4640 part 1 tables. And then thermal conductivity maps for Europe were created for that. Because we wanted to look into the market, not just what is the underground of Europe, but what's the underground there where people want to have these kind of systems. There was a weighing process with thermal conductivity by population density to get these market potential into the picture. What you see here, the to the left, the 14 geocond lithologies. If you use this kind, let's say this basic resolution for the map of lithologies, and to the right, the derived map for the thermal conductivity. There is a caveat to be made. The thermal conductivity of porous rocks is quite dependent on the water content. And this is something that we couldn't include because there is not sufficient information available on that. The area covered is the EEA countries. UK was still part of EEA when we did that. Plus Switzerland, Balkan countries that are not, and Turkey and Israel because they were geocon partners in both of these countries. Now, what happens if we are looking at the population density? You see here the dots. Each dot represents 200,000 inhabitants, and we see that there is a clear picture that we have areas with high population density and some others with very low. And in particular, if you look here at Scandinavia, you see the areas with very high thermal conductivity ground. They're very good granitic rocks and this kind of thing, but there are no dots at all. As a result, what we see here, if you are doing some statistics from that, look at the thermal conductivity classes. Each class is 0.5 watt per meter Kelvin. The blue, no, the orange or brown, light brown columns give you the percentage of area. And when weighing that with the population, the light blue columns come out. So for the overall study area, the main ground conditions are somewhere in the 2 to 2.5 region. The one that was 2.5 to 3 in the area is in practice for the population quite small. And for the higher ones up here to 4.5 to 5, there is almost nothing. You can't even see the light blue parts here. It's more understandable when looking at individual countries. I think Sweden is the most striking example, where there is a lot of rock with high thermal conductivity, up to 3 or even above 3 watt per meter Kelvin. But when looking at where the people actually live, most of them that are not living on top of these high thermal conductivity rocks. Still, there are quite a few, but much less than with the area. So taking that into account, we did some, or at UPV, some, let's say, modeling was done, a huge number of quick simulations with EED to understand the influence of pipe and grout conductivity. So this is grout thermal conductivity. This is pipe thermal conductivity. The required bore length here, or in this case, I think it is, well, what value do we have here? Yeah, well, it's a measure of efficiency we've used. You see with very high grout and pipe conductivity, which is up here, we get good values, but actually an area where we have an optimum in here. This, of course, is the lowest, where we have low pipe and grout conductivities. Each of these has to be calculated for a certain ground thermal conductivity, and the statistics done before allowed to limit that to certain classes only. So from that on, I think the next one will be the part 2 by Adela, explaining what started from that on, because this is what we needed for Geocond, for the further development of the materials. But this tool has more to offer, and Adela worked on that to continue these activities. So Adela, please take it.
Okay.
You can now directly share your screen, Adela, if you like.
Yes.
It will turn over to yours.
Okay. Can you see it now?
Yep, perfect.
Okay. So yes, hello, good afternoon, everyone. Following the Burkhard part, I'm going to show you the work that was done apart and following the Geocond project to turn the spatial proposed maps into more holistic resource mapping. So this was a work done between the University of Valencia and the University of Cartagena. It's a bit slow, I think. No, yes, no. So the study consisted on a pan-European spatial assessment of the physical environmental indicators, determining the performance of shallow geothermal energy closed loop systems, and the final creation of a series of thematic maps. So the figure that we can see here shows the GSpace stepwise methodology that was carried out for the creation of the different maps. I don't know if you can see it properly, but I will explain this information in detail. So looking at the first step of the figure, we can see the different indicators that were included and considered related to the geology, to the climate, and to the environmental protection. In the second row of the figure, we can see the baseline information that was considered for every map. The third step comprises the data processing in GIS and the possible extra information that was used for every map. And finally, the fourth step includes the outputted maps. So let's have a look of the maps. So within the geological setting-based indicators, we have the thermal conductivity and the consolidation rate material. This thermal conductivity map is that Burkhard was mentioning in his presentation. So both maps are based on the International Hydrological Map, which is openly accessible in the European Geological Data Infrastructure. This map provides geological information at 5 different aggregation levels, from Litho 1 to Litho 5. Litho 1 is the most detailed, provides the most detailed information, while Litho 5 gives the most basic group information. So thermal conductivity values used were extracted from the BDA, from the German standard BDA 4640. So in order to link the spatial information from the hydrological maps to the thermal conductivity values, the geological information was first reclassified by using 3 aggregation levels from the hydrological map, which were the Litho 4, the Litho 2, and the Litho 1 information. So once the new geological layers were obtained, the thermal conductivity values from the BDA were linked in a GIS environment to the new geological classification. And then the thermal conductivity map was then obtained. Just to point that for linking the attributes for one layer to the other, the join tool available in ArcGIS program, which was the program selected, was used, which is available at the Geoprocessing Tools package. So to proceed, again here for the consolidation rate material map, the lithological information from the hydrological map was used, but this time Litho 5 aggregation level was only needed, as it provides directly a classification division referring to the degree of rock consolidation in 3 groups: the unconsolidated materials, the partly consolidated materials, and consolidated rocks. So in this case, no extra processing or data was required. So finally, we obtained the consolidation rate rock map, just displaying this information. And we think that despite the simplicity of the elaboration of this map, it is considered a crucial information. As for instance, it helps to determine the most suitable drilling technique at a European scale. So regarding the climate settings mapping, we consider the ground surface temperature, the annual thermal amplitude, and the heating plus cooling maps. This is the ground surface temperature. And for its creation, we took into consideration the assumption of Signorelli that pointed out that ground surface temperature depends linearly on the altitude and is equal to surface air temperature up to 1,000 meters above the sea level. And above this altitude, ground surface temperature is affected by a difficulty forcible local deviation ranging from 1 to minus 2 to minus 2 Kelvin degrees. Thus, here the baseline information was the digital elevation model. So in a GIS environment, the process consisted on the reclassification of the altitude raster map in 3 classes. One with values ranging from 0 to 1,000, another with values ranging from 1,000 to 1,500, and another with the rest. And then every class was assigned with 0, 1, or 2 numerical values, and then a new raster was obtained. Finally, these values and those from the surface air temperature layer were summed by the raster calculator tool, which is available at the spatial analysis package of ArcGIS. So finally, we could display this information in the ground surface temperature. Next, the thermal amplitude map. This map shows the difference between the mean warmest and mean coldest annual temperature in the Europe. In the European countries, the warmest and the coldest month turn out to be the temperatures of July and January. So one raster was created with the temperature of the 2 months. So process in GIS consisted on the difference of these 2 layers by using again the raster calculator tool. The information of this map, we think it's of great importance when it comes to determining the suitability of providing the space heating or cooling with ground source heat pumps compared to the more conventional air source heat pumps. The heating and cooling degree days are important assessment indicator as well, as they offer a rough insight about the energy demand to be expected to heat or eventually to cool a dwelling. So this time, heating degree days and cooling degree days data was extracted from the Eurostat database. The Eurostat provides this information at different administrative levels. And for this purpose, we selected the NAT2 level, which is approximately a regional level. So in order to create a layer, a complete layer covering the whole territory, this data had to be interpolated. So we used the gridding tool, which is available at the interpolation toolset of the geostatistical analyst extension of ArcGIS. So at the end, we summed the 2 layers, the heating and the cooling degree days, and we obtained the heating plus cooling map. So looking at the maps, in areas where heating and cooling values are low, the demand expected is lower than for the equivalent buildings with higher values. And finally, we also created the protected areas based on environmental indicators. So this approach was carried out in 3 steps with 2 main data sources were here considered, which were the European Environmental Agency and the International Union for Conservation of Nature. So in step 1, the spatial information of the protected areas was collected from the European Environmental Agency. This information was directly provided in this layer and contained information over superficial water and nature protected according to national legislation among the different European countries. So step two, involves the collection of the data from the International Union for Conservation of Nature, which contains the same data as the European agency, but this time it provides a new classification according to the management approaches of these protected areas. So at the end, this classification summarized the 275 groups provided by the European agency into 6 management categories. So finally, the first step provides another classification, what was created for us, based on the likely restrictions in permits and for the exploitation of the shallow geothermal energy. So among the 6 categories, the first category encompasses areas strictly protected, and thus no human activity was allowed and were considered for us as not allowed protected areas. The other categories encompass some kinds of protections that may limit the human use in this area and were considered in this approach as areas where the shallow geothermal energy exploitation may be restricted. And rest of the areas then were understood in principle to not present any restriction at such scale and were categorized as non-protected areas. So finally, all of this information was displayed in a map, and we obtained the protected areas map. And finally, we consider that the resulting thematic maps not only contained relevant information itself, but they also could be used for more practical approaches. So we also proposed this based multi-criteria decision-making approach with our thematic maps as inputs. For practical reasons, we used here only a regional case, and the approach finally resulted in a suitability map for the exploitation of the geothermal energy. And as an example case, we selected the area of region of Murcia, which is located in southeast Spain, that we can see here in the map. So to proceed with the approach, the criteria must be weighted. Weights of the criteria represent how they influence to determine the areas where ground source heat pump will perform with the best results according to the understanding of experts. The weight was obtained by applying the analytical hierarchy process, which is able to output the expert opinion in numerical values. So these values allowed us to order the criteria from the most to the less important, as we can see here in the table. So next step of the approach was the normalization process of the criteria that allow us to compare criteria to each other. Following, values from each criterion were segmented in 3 categories according to their suitability to reach a goal, and we assigned a score to the categories: 1 for the category considered acceptable, 2 for good, and 3 for excellent. And then a weighted sum was processed in GIS for every pixel of the map according to the formula here presented, using the map algebra raster calculation function. With this formula, every criterion weight represented by W was multiplied by its criterion score represented by the letter S. So at the end, we get a resulting map, which is a new raster containing values ranging from 0 to 3. So to translate this information into the suitability map, areas with values between 0 and 2 were considered acceptable. Areas with values between 1 and 2 were considered as good, and 2 to 3 as excellent areas. So looking at the suitability map, here we can discern some areas with excellent properties, but in contrast, we know that the regional government does not give any mention to the shallow geothermal exploitation in the regional plan. So we think that these resulting maps could be a good tool to support the energy decision makers, to propose to promote the use of the shallow geothermal energy at the regional scale. And just concluding, just to say that this approach provides a tool that can be applied also in other regions contained in the pan-European thematic maps here presented. And it can be also completed and supported by additional regional spatial information as well. That's all. Thank you very much.
Thank you very much, Adela. Very, very interesting presentation. Thanks to both of you, Burkhard and Adela. There are a few short questions for the understanding, and there are some which I will keep for the discussion round.
Okay.
The first question to you, Adela, was by Johannes. If the maps will be available as a shapefiles anywhere, so can be used in future projects.
Yeah, it will be accessible in a short time, I think. I hope maybe before the summer, but not in shapefile, but in raster file, in the EGI, in the European Geological infrastructure that I mentioned and Burkhard mentioned online.
Yeah, I would like to add on this that EGDI is a product by Eurogeosurvey. So also the MUSE project will feed its result into the EGDI environment, and we are trying really to capitalize the existing infrastructure in the future of EGDI to provide such data with open access, of course, in the future, also from European projects which have a dedicated end of lifetime, and we as Geological Survey would like to take care about these data sets also in the future. Then there was one quick question. Your prediction of thermal conductivity, was it validated against TRT measurements? Did you have some validation points for the prediction? And the prediction itself, was it referring to existing guidelines like the VDI, the German guideline?
Yes, the thermal conductivity values were extracted from the VDA guideline, as Burkhard also mentioned. But I'm afraid they were not validated with in this study they were not validated because it's at the European scale, so it was a kind of difficult task.
Yep. No, I guess it's difficult to get access to these TRT measurements by mostly private companies.
Well, so sorry for jumping in here. Of course, we have a lot of this data because we are one of the companies creating those. But as Adela said, on this scale, it doesn't make much sense. So that will be something when you go to regional scale, like here from Murcia or other places, to look into TRT to get it. It was just simply done by VDI, and we later discussed also the question of the water content and these kind of things. So there is, of course, some error in the whole process, but it was justified, at least for the Geocond project. I can explain that later on. Yeah.
Thank you very much, Burkhard. I think all the other questions we will keep for the final discussion and question round, because it might be more to discuss and comment on it. Thanks a lot for your presentation. And I would like to introduce now my colleagues. So just see if I can share my screen. Here we go. Coming to the second presentation, done by my colleagues Cornelia Stein and Martin Fuchsluger on this national project GEL-SEP and the use of G-functions inside for borehole heat exchanger mapping. So I would like to ask Martin to share your screen, and the floor is yours, Cornelia and Martin.
Yes. Thank you very much. I'll try to share the screen. One moment. Okay, does it work?
Martin, yes, but you have to switch the view. You're still in the presenting view, what you did before when we tested it.
It's the same as before, okay.
Now
Now it should work. Okay.
Yep. Great.
Yes, thank you very much. It's very interesting. We are faced with the same stuff by creating maps for conductivity, and so I will present you today that application of the G function for resource mapping for the project GEL-SEP. And I ask Cornelia, she will introduce the project in a few slides.
Yes, hello from my side as well. I'm happy that I can tell you more about our project spatial energy planning. We have some similar ideas or problems more or less that we discussed in our project. So spatial energy planning is funded by a national funding agency, the Austrian Research Promotion Agency. It started in 2018 and it will finish this year. And the goal of this project is to develop a web tool called Energy Atlas that will provide information about renewable energy resources, the heating demand, and also the energy supply infrastructure. And we, from the Geological Survey of Austria, have been asked to look into shallow geothermal energy. And so we developed methods to calculate the resources for borehole heat exchangers, for groundwater heat pumps, and for surface heat collectors. And in this talk today, we are going to focus on the borehole heat exchangers. If you're interested in the other systems as well, then we can talk about this later, maybe. And so we provided this information for our pilot areas. They are located in the city of Vienna, so it's the entire city of Vienna, certain areas in Salzburg, and some locations in Styria. And in these pilot areas, we provide two main categories of content. The first are possible limitations of use, and the second are energy resources. And those two categories are going to be provided in three tools for the Energy Atlas. Tool number one is a map viewer that shows resource maps and traffic light maps. Tool number two is a location-specific query that focuses on properties. So if the user clicks on a property, then he or she will get an automatically generated PDF report that summarizes all information from tool number one, but also some specific calculations for the properties. And tool number three is more on a regional level. It is an analysis especially for city districts or for municipalities, also in form of an automatically generated PDF report. And so all those tools will provide information to integrate heat into spatial energy planning. And now I'm going to present to you those different tools in a little bit more detail. And Martin later on will present to you the method and the workflow that is behind those results. So for the traffic light maps, at the first step, we identified possible limitations of use that could limit the applications, for example, water protection areas, also flooding zones, and so on. And then we categorized them in three classes. First one means generally not possible. So it will not be possible to use the certain system at this area. So we develop those traffic light maps for the different systems separately. So there is one map for borehole heat exchangers, one map for the groundwater use, and so on. The second class means that there is more information necessary. It is not strictly prohibited to use the system in this area, but there might be troubles or problems that one has to look into. And green means that there is no limitation known at the moment, so it is generally possible to use the system. And then this traffic light map combines all the different layers into one map that shows always the strongest color. So pink over yellow over green. And this is one example of the traffic light map for the city of Vienna. And you see that pink areas are only very small ones, mostly related to water protection areas and underground buildings. And for the resource maps, we provide basic information about the geology and the climate. So we also prepared a thermal conductivity map for a depth interval from 0 to 100 meters. We calculated the mean annual underground temperature also for the same depth interval. And then we looked into standardized operating hours for heating and cooling. And those operating hours will later on go into the calculations for the capacity and the energy content. The thermal conductivity maps are especially important for the designers of the installations, but also energy planners are part of our stakeholder consortium, more or less. So they are more interested in how much energy is available and what about the heat extraction rate. And so they kind of pushed us or really encouraged us to also provide information for those two parameters. And the reason why we have been a little bit reluctant at first in providing this information is that the borehole heat exchangers really depend on certain system configuration. Martin, please go on. And so if you want to calculate the energy or the capacity, it really depends on the length of the borehole, the number of boreholes, the distance between the boreholes, and the operation mode. If you're going to use it for heating and for cooling or for both, and for how many hours per year. And so if you want to calculate those parameters, you have to fix the system. And the other way around, this means that our maps are still, strictly speaking, only valid for the system that we have selected for the calculation. So, but anyway, we decided to choose certain systems, and then we calculated for the, could you go back one more, please? Time, yeah. So we selected for the specific capacity a singular borehole heat exchanger and calculated it for two modes of operation. The first one is heating and cooling with standard operating hours that depend on the climate. And the second one is a balanced mode of operation where the borehole heat exchanger is essentially used as a storage. So it is used for the same amount for heating and for cooling. And for the energy content, we went for a borehole heat exchanger field with the same modes of operation. So also with standard operating hours, and the second one with the balanced mode of operation. And the second, so we now come to the tool number 2, the location query, where you select a certain property, like this is shown in the example, and then you get this report that lists all kinds of information, starting with some basics about the property. For example, how large is the property, how much free space is available, and then we can also include demand or the demand of the building, and we provide some basic information about the geology that is taken from the tool number 1. So this is basically also the heating and the energy content and the specific capacity, and as I said, the geological information from tool number 1. And then we have the specific calculations that look directly on the property. At first, we take a look at the demand and calculate how many borehole heat exchangers would be necessary to meet this demand. And then we take a look at the resources that are available at the property. So we calculate how many boreholes you can actually set up on the free space that is available. And then we combine these two calculations together to come up with the coverage of demand. And the last thing that is included in this PDF report is also information about possible limitations of use. For example, if there is a water conservation area available, then you get some information text in the PDF report. This is taken from tool number 1 as well. And then we have one more tool, the tool number 3. That is only some basic information that I have for you at the moment, because it is still a little bit in development, so to say. So we are going to provide an overview of the total resources in a city district. This means we calculate the overall energy content that is available. But in this case, we take into account the pink areas from our traffic light map, because we know that it won't be possible to use the shallow geothermal energy system in those areas, so we exclude them from the energy content calculations. We can also calculate the amount of coverage that is taken from tool number 2. And then we basically will also show some kind of suitability for the area that at the moment is intended to basically be the traffic light map for the borehole heat exchangers. For the groundwater heat exchangers, this means that we take into account the where groundwater is available and where it is not. That is a little bit easier for the borehole heat exchangers because it essentially works everywhere, more or less. Yeah, so that was my brief introduction to the project, and now I hand over to you, Martin, to tell us more about what is behind those calculations.
Yes, thank you, Cornelia. This was the overview of the project GEL-SEP. Now I will show you how we calculated the maps and the location query informations. So at first we look again at the requirements for the project, what is asked. And then I will show you the background to the calculation with the G functions. Further, I will show you the calculation tool we developed and the workflow of it. How does it work and what does it do? And then also some details about the calculations, which are interesting. And at the end, I will present you the maps and the queries. Cornelia already showed you some basics. Yes, so for the project, 3 tools was requested. So this tool 1, we already heard, the resource map viewer. So the purpose of this viewer is not to for the measuring of the borehole heat exchanger, it's to compare the locations. So we can fix or set fix systems, and so the main dependencies of this of the outputs is the underground temperature, heat, conductivity, and the climate. We use the standard operating hours for that. That means how much do you have to heat or to cool on this location. So on the location query, it's the other way around. So it's then important you have a building with a certain demand, and it's a first dimensioning tool for the buildings. And second, it's interesting how much potential and power and energy is available on the property, on the free space. And with these two informations, we can calculate the coverage, which is an interesting property. And the main dependencies on this tool is, of course, the power demand of the building, which dimensioning the field size and the influence of the field, and next to the underground temperature, heat conductivity, and also the seasonal performance factors, here is CUP, is important, and the available free space. So for the communities, it's important in my communities how much energy I can use in total in the whole area, and where the coverage is good and not so good. So it should give, this tool should give an overview, also in form of a report of the community, of the total available potential. So here, the most dependency is how the spacing, how far I can set the spacing or how narrow, and the field size also. I'll show you later more about. So the skills for the calculation tool should be flexible to many input parameters. It should go fast in calculation. That means we look for analytical solution, and it should be suitable for all three tools. So we decided to use the G functions for the calculations. This formula show everything you need to know about how to calculate the power of a borehole heat exchanger. So the power is dependent on temperature difference of fluid and the earth, the heat conductivity of the earth, the borehole resistance. So temperature difference and heat conductivity are dependent on the location. Borehole resistance is dependent on drilling depth and grouting and so on. And the last thing is the geometric function. That means it's not necessarily dependent on the location. It's dependent how far you set the spacings, the length of the borehole heat exchanger, how deep you can drill, and how much you need next to each other, how much borehole heat exchangers, yes. And also the time, the operational hour, how long will it be in operation, play here a major role. The longer the time, the operation, the lower the power you can use. And also the thermal diffusivity of the earth is an important parameter, play also a role in the G function. So that you maybe can imagine what a G function is, I have plotted here one G function for a very simple case, for a single borehole heat exchanger for 4 different heat conductivities from 1, 2, 3, and 4. And you see the G function theory was developed by S. Kilson, and it's based on a finite line source theory. That means the G functions describes in general the resistance of the earth for a specific configuration. And the trick of S. Kilson was to make the X, the dependency of the time, dimensionless. So he introduced the S. Kilson time with this constant, which is dependent on the borehole length and the earth parameter. So it's at the end, the G function itself with this trick is independent of the material property of the, and so it's only dependent on the geometry. When you calculate the power for different conductivities, for example, you see the graphic, you get different power lines with the same G function because it's just shifted in time. That means it's getting in high conductivity, it's much faster. The wave is much faster. One important note, what Kilson said was that at this time, ES1, that the vertical heat flow is neglectable, means below 7%. And when the Kilson time gets 10, it's the temperature wave gets stationary. That means it doesn't change anymore. So when we look at the simple common example with a length of 100 meter and thermal diffusivity of 1 to -6, it needs 35 years of operation permanently that the vertical heat flow is neglectable, and it needs 350 years of operation that the heat propagation gets stationary. So this example just show how slow this works and how long this process needs. Here you see another G function for 2 boreholes with different spacing to depth ratios. And just to show you, it's possible to calculate the G function for really many also complex geometries, also circular arrangements or inclined or sloped drillings. So one thing about the G function, one more thing which I like is the superposition principle, because with that it's possible that we can also simulate a step function, not only permanent operation. This is a really simple step that we use heating 2000 hours per year, and then it's a natural regeneration, then heating, regeneration, and so on for 3 years or 4 periods. And I just show you it's then really simple to calculate. You just need the G function at these points where the step is changing, and you just have to add them. In this case, we have 13 degrees of temperature difference we can use, and we get a simple formulation, and that means this result shows we can use 33 watt per linear meter at this location, also at the end of the 4th period, of the 4th heating period. We checked also how this fits to the standards. This is an example of the standard norm in Switzerland, and for example the heat dependence of the heat conductivity of a single borehole heat exchangers. It fits very well. Yes, so as I said, the power is really easy to calculate when the G function is known, but to calculate the G function is not so easy. So how we get the G function was the question, and my research in internet showed that there is already a tool available. It's called G function, and it's developed from Massimo Cimino. You can see the citation below. It's really impressive tools. You can make whole simulations of borehole heat exchanger field in really quick time, and I use just to calculate the G functions. We will see later on. So the next step was to the workflow now. We developed a tool. We call it BHEs or BHEs or nickname SEPI. It's, by the way, a common nickname in Austria for GEL-SEP, but it works in general simple. As inputs, we give the underground parameters, the parameters of the property, so the free space, and the building demand, for example, and the output is in general the specific borehole heat exchanger power in watt per line meter. Yes, so the script is in Python, as the G functions also, so it's platform independent, easy to implement, and we have a flexible parameter configuration. Now I'll show you the inputs we need for the calculation for the location query in detail. So it looked like a little bit more complex. So we need, as Cornelia already said, fixed parameters, fix the constant parameters. We take limits for the brine, minimum, maximum from minus 1.5 to 25 degrees, lifetime or operation time of 25 years, and borehole length in general 100 meters. And here you can set also the spacing for unbalanced and balanced use. The borehole resistance we have to set fixed, and the mean heat capacity of the earth. Generally from 0 to 100 meters is most time around 2 or 2.3. And then we need the underground parameters for the property and the building demand for the property. So this is for every property different. You can see here an example in the brackets. So I put, you can see the U in the end of the application. This, for example, the free space, the heating power, the operation hours, and so on. The seasonal performance factors should be changeable interactively by the user who makes the location query. That would be our suggestion as possible. And the tool BHEs first checks if it's balanced or unbalanced, dependent on the input. And then it set up the load function for 20 years or 25 years. I think it's 20 years now, with heating, cooling, and natural regeneration. That means 4 periods every year for 20 years. And we look at the end of the year, what's possible at the end of 20 years, which power is possible then. And it makes an iterative calculation with Apache functions. So what's the output of the location query? We already saw this, how much power per line meter. In this case, it's 30.9 watt. And you need for this demand, building demand, 3 borehole heat exchangers with 127 meters, which needs a free space of 69 square meters. The next is we calculate how much power is possible when you set all your free space with borehole heat exchangers. This would be in this case 11. The power drops to 26.4 watt per linear meters, and so we can calculate a coverage between what's possible, maximum possible on this property, and what's needed. In this case, it's 3 times more what's possible than needed. Yes, this is the location query results Cornelia already showed us. It's just another example. We don't have to go further. So small details. How does we make the conversion of the number of borehole heat exchangers and the area which is needed? This is dependent on the spacing. So we decided to use a most compact arrangement. That means on the edges we use 2 meters to property and building, and then the spacing as it is given. For 10 meters, for example, you can see for 1, 2, 4, and 10 borehole heat exchangers how much area they need. So we don't set the points in the free space. We just calculate it from the area to the number of points, and vice versa. The next thing is the standard operating hours. This is an important parameter. That means we thought about to use heating decrease days and cooling decrease days and so on. And so we, at the end, we took the standard operating hours, as it is also in the Swiss norm the case, but we modified it a little bit. In the Swiss norm, the dependence is on sea level, and we decided to recalculate it from the mean surface temperature because it's easier for us. So you can see the curves. One is for heating, and domestic hot water, and the other is for cooling. That means the higher the mean surface temperature on this spot, the lower the standard operating hour per year. It's designed for one-family houses, of course. And the cooling is a professional solution, maybe changed to further releases. We said below 8 degrees, it's not necessary to cool. And the higher the mean surface temperature, up to 14 degrees, it's about 1,000 hours per year. That's the functions behind. And also the load functions you see here. Every calculation, we use a load function like this. The tool SEPI, look, it's more heating energy or more cooling energy needed. When more cooling energy is needed, he begins with cooling and ends with cooling. So it's the more conservative calculation function. In this case, we see here, we begin with heating, and cooling is lower demand. Yes, and at the end, we also have to know or estimate the seasonal performance factor. And this is, from the building data, we don't have information about the heating distribution system. So we decided to use a simple approach and connect it to the construction year and estimate the heating temperature and take a source temperature of 2 degrees for borehole heat exchangers, and gets at the end seasonal performance factors from 2.3 to 3.99, which are also considered. This may be improved in future, but for the first time, it's I think okay. And this is one result for many properties. When you calculate all properties for a region, you can plot the coverage. You see here, green means coverages are more than 75% or more, and orange is below 25%. And this is also a good information for tool 3, for the regional summary, that we give a statistic how many of the properties has which coverages. And now I think we have to hurry on. I show you the calculation for the maps is a little bit different. We also use the tool SEPI, but with a little bit other inputs. So we fix 3 scenarios of borehole fields. One is a single BHE, one is a field with about 1,000 square meters, and the other is a really big field. This is just for tool 3 for the general summary. And as we don't have building informations for the maps, we use the standard operating hours per year for heating and cooling. And so the tool, in this case, for whole Salzburg, for example, we have more than 700,000 points to calculate. So we calculate this for every raster point, and we approximate the G function here, first calculated with high G function, and then we approximated with a polynomial function with 12 or 13 degrees. Genau. Yes, and the outputs we have at the end 6 maps for tool 1, 4 maps which give the power for single borehole heat exchangers, for balanced and unbalanced mode, and the energy for a 1000 square meter field, also for a balanced and unbalanced mode. And for tool 3, this map is hidden. It's just for the regional summary and overview to include also that everybody can use borehole heat exchangers. So some more details I prepared, which I think it's really interesting, because you see here 2 graphs. The left one is the borehole heat exchanger energy, and how does it is dependent of the yearly operational hours. You see for 3 modes: for heating only, for heating and cooling, and for storing. And so you see for storing it's much more than for heating and cooling, because the spacing is 5 meters and not 10 meters. That means the higher the operating hours per year and the higher the spacing, the higher is the energy. The lower the spacing, the higher is the energy harvest. Yes, but on the other hand, the lower is the specific power. That means the specific power gets down to 20 watt per linear meters if you have much operation time per year. And this also interesting graphic, I think, because it shows also for these modes how does the energy is dependent of the field size. That means we decided for the regional analysis that is efficient when we take 400, a field size of 400 to that we can sum over the whole area for all clusters. Yes, at the end, I will show you the results for one area we calculated. It's in Salzburg, the example. You see here the input parameter for the mean underground temperature. You see it's a really mountainous area with it's the highest mountain also here from Austria with nearly 4,000 meters. And yes, this is the other input is the mean thermal conductivity from 0 to 100. So you just see the map on the long-term settlement area as in Salzburg, we produce the maps just in the settlement area, the long-term settlement area. And you see here in the mean conductivity clearly where the sediment basins are. These are the areas with the lower conductivity between 1 point, the brown conductivities. And the blue ones are in the hard rock area. And that's the same. Most of the population is in sediment basins here in lower conductivities. I show you then also the map for the standard operating hours per year for heating. This is also an input for the tool, and the standard operating hours for cooling. You see the white areas has no cooling demand for standard operation. This is the first result map. You see the specific power for single borehole heat exchanger with standard heating and cooling. So it's up to from 20 because it's very cool there, up to 42 because it's warm underground and good conductivity. And this is a similar map, but just for storage. So in general, the power is a little bit higher. It's for balanced heating and cooling. This map is energy map. That means we take a borehole field of about 1,000 square meters. That means for heating and cooling, it's 16 boreholes, and with a spacing of 10 meters for standard heating and cooling, you get from 40 to 90 kilowatt hours per square meter and year. And also 1,000 square meters for storing with 5 meter spacing means 49 boreholes or 7 by 7. Also with balanced heating and cooling then, and it's much higher energy. You can use much higher specific energy, and that's also that should be that we want to show that with storage you can use much more energy, but maybe you have a lower power. And yes, here the last maps are the hidden maps for just summarize for all areas. I cannot show you the results of the summarization now because it's not done, but it will be soon. But this will be the basic for the summarize of for the communities. And we take a huge field for the calculation. You see also here, it's the maximum is 50 kilowatt hours per square meter and year. So the influence of the neighbor is included here for sure, you can say. And the same for balanced heating and cooling or storage. It's much higher energy you can use because you recover every year the temperature full again. Yes, that's the end of my presentation. Just short summary and outlook. We think that this tool with the Apache functions is a good tool for all requirements for our project. The workflow is ready now to implement in the Energy Atlas. And actually we organized a handover to the implementation team because it's not done on the Geological survey, it's on more technical. And maybe we have some small improvements then after feedback for optimal handling, and then the Energy Atlas should be ready, I think, to use in autumn. And we think about to prepare a publication of the BHE-SEP tool for public free use. Yes, thank you for your attention. Sorry for the time delay. I'm ready for discussion.
Thank you very much, Martin and Cornelia. Very interesting. Before we lose most of our participants, but I invite all of you to stay a little bit longer with us so for discussion, because I think there are a lot of things we should discuss. But before I come to the final Q&A round, I would just like to say show you, sorry. Where are we now? Close. Sorry, just wanted to show you another thing. Just activate my presentation. Here we go. Because there will be another probably interesting webinar in a few weeks, and I just want to inform you about this one. So the EuroGeo survey or GeoEra will organize 2 workshops on geothermal energy together with United States colleagues. They both will be quite close to each other. On June the 8th, there will be a geothermal session jointly organized by USGS and EuroGeo survey on bridging geothermal energy to the next level. So it's a lot of, not on just on shallow, but also on deep geothermal from the point of view from Geological Survey of the United States and Europe. So it's also about the strategy in the next decade. And there is one special workshop on the 14th of June where we look at urban geothermal energy use, but with a special reference to shallow geothermal. And the list of speakers, they are almost finished. So we will have at least 2 speakers from the United States. And it would be interesting to learn how do they do resource mapping and managing of shallow geothermal, mostly groundwater heat exchangers in the United States. And We have more speakers also from Europe, from the MUSE project, like Alejandro Garcia from Spain, or colleagues from the TU Munich, which have very intensive monitoring network in Munich. This is just for, yes, if you're interested, here you see the web link. You can also write an email to me and I forward you the registration link to this event, which is free of visiting. So this was from my side. Let's go to our final question and answer round and our discussion. So I really invite you to stay online for a few more minutes. And I would like to start with some short questions for understanding to Martin and Cornelia on their project. There was the question of how did you distribute the locations of the BHE inside the free space? Was it just calculated by assuming an optimum configuration by dividing the needed space and the available free space? You mentioned a few criteria like minimum distance to buildings and the land property, but did you apply any other algorithm?
No, yes, indeed, we just make this hard calculation from area to number of borehole heat exchangers with a compact field. That means it's hard enough to get the free space, because from the map it's not really clear which space you can need. This is another challenge to get the free space, and so we decided that the calculation to the borehole heat exchangers is not so exactly, has not to be so exactly.
Okay, let's go back to another topic which was raised by myself also before, according to the presentation of Burkhard and Adela, and it also refers to your work. So my question first was, in the presentation, you shown, Adela, that you didn't consider, of course, the water field content in the subsurface rocks, and you used the EGDI maps. So which kind of maps would you find helpful in the future to amend predictions from a geoscientific point of view, not from a methodology point of view?
Adela, you seem to still be muted, but maybe I can.
Yeah, thank you.
If you allow me, I would like to shortly answer here to Gregor, because for the Geocond project, this was okay, because as long as the thermal conductivity is not above some 2.5, it's not interesting, so much interesting for us. And this is not the case in any of the porous materials. The other point is, we would need, of course, as you said, the groundwater table to see if there is groundwater in or not. But that brings us to another problem, which is the third dimension. The maps don't have normally this third dimension yet. We don't have 3D models. So, and also these groundwater table maps are available on a local or regional level. So this is the problem for that. But Adela, you may have more ideas than that.
Oh, well, yes, I just used for regional approaches, as I showed you before, I used the water level maps for this purpose. So unfortunately, they are not really common in Spain. So maybe for some regions, but I had to do it by myself. So I don't know publicly information about that.
But you would, for instance, use water table maps to calculate the sea velocities for estimating any kind of non-conductive effects. I mean, this is also a methodological problem, I guess.
But it's for me or for Burkhard, the question?
Anybody who wants to answer.
There was a second question to Adela also, or was it? No, it was to Cornelia, if the groundwater flow is taken into account. This is something that's very, very special, because again, we are now on a completely different scale. So that only can be done on a very local or regional scale to include this. So that's why we've decided to look only at the conductive heat transfer, which is for a borehole heat exchanger the most important part. To really have an impact from flowing groundwater, it requires well, quite some high RC velocity to make that visible.
We also ran into the problem of data availability for the groundwater tables, because we cover different areas in the cities. There are groundwater tables available, but we have also the more rural regions, as you have seen on the map of Salzburg, and at some areas there is not even a groundwater table map available, so we had to improvise in these topics as well. And the idea was to develop a harmonized method that can be used for different data availabilities.
Yeah, and in particular for the I reckon you will have to redraw your water table maps year by year, because the groundwater table is dropping down by over extraction, isn't it?
Yes.
Yes. And climate change. You also see this one. Yeah, both. So this must be intelligent, yeah, or continuously or not frequently updated information systems. Just
that's
concerning
that's also the purpose of the GEL-SEP project, that it's not a fixed map, so it should always be have access to the newest informations about groundwater. We have also the groundwater potential maps, and to also heat conductivity should be changed maybe every 5 years, updated every 5 years or so. And on heat conductivity, I saw also the problem that some high conductive zones are really small islands, so you don't know how deep they are going in depth. So of course the best thing would be to have a 3D model of geologic fluids.
Maybe I want to comment on this for the future outlook on the EGDI. So in the moment, everything is 2D, and it will stay for the next years, unfortunately, because it requires a lot of resources. But EuroGeo survey is applying for Horizon Europe funds, coordinated support action dedicated to strengthening the network. And they want to move towards the third dimension in EGDI, and it will be available. It will probably take a few more years, starting of course with geology and then going into geoscientific parameters in its 3 dimension. But it will be available, but it's not for now in the moment. And if we stay at the 3-dimensional problem, I would like to ask Adela, because this question was raised about any complex geological conditions. Could be anhydrites, could be salt layers and so on. So did you try to consider such let's say difficult geological conditions as well in your maps as an suitability evaluation?
No, not in this work. We just went into the lithological information from the BDA, from that geological information provided in this German standard.
Because this is also a problem, and we need to have these layers in 3D. 2D maps will not be sufficient, and hopefully in the future we'll have a stronger data information system, so such information can be also tracked in a third dimension.
Yeah, I think because we all only worked in 2D dimensions, so we couldn't scope this problem. So we just work with the outcropping geology. So indeed, that will be a further step in this approach.
And Then was a question to Cornelia and Martin once again, a very important one and a challenge by itself is about neighboring influence. Have these neighboring influences been somehow considered or can be considered in your workflow, meaning that there are already BHE existing around?
Sorry, yeah. Yes, it could be. We did not see here a big problem because the influence is usually just 10 to 50 meters, usually, I say without groundwater, but so most time between the properties and there is some space somehow that this will not have a big impact. But of course, if some neighbors directly next to each other, the maps will and the location query will maybe overestimate a little bit.
Mm-hmm.
And the summary for the whole area then includes this influence because we calculate the potential, the energy maps for really huge fields. That means that's nearly the maximum influence you can have. So, but this only works for big areas.
Mm-hmm.
For summarization of big areas.
Mm-hmm. But do you think your workflow could be adapted also allowing for taking into consideration neighboring influence? It might be a question of setting the boundary conditions, so meaning the temperature and the subsurface.
Yes, of course.
Mm-hmm.
In general, you can simulate with this tool also 4 or 5 neighbors together, you know, and give the potential. Or in another case, you can set another temperature, maybe subsurface temperature, and influence temperature.
I see, Johannes, you raised your hand. You would like to comment? Please use the microphone.
Yes, can you hear me?
Yeah, we can hear you well.
Yeah, sorry for all these critical questions. I've just finished a similar study for a state of Germany, and there I also have all these issues. So how do all the neighbors influence borehole heat exchanges on one property and so on? And I think the key message here is it doesn't really matter if you're over or underestimating the energy that you can get out. The key is just you have to communicate that what you present there may not be the reality. Because on the end of the day, when the end user is maybe looking for his or her own house and wants to know, will borehole heat exchangers make sense for me? They need to know that this doesn't really give them the real data that they will then get. But other than that, great work. I think it was a really nice presentation and great maps.
Thank you. Thank you very much, Johannes. Yeah.
Just a comment. I think it's the same. I think the same. It's just really a first guess that people get involved with it and that they can have a first dimension of. We should write everywhere that experts have to make the real dimensioning, and it can be different.
Well, this is always important to have this kind of disclaimer. We were using in Geocond also on a decision support system that uses maps and add some of the Geocond materials to give first indication could be done in a certain place. I know that Geophysics is working on similar DSS and other projects also have it. They can give only a very rough first impression, but each plant must be designed for the individual site and looked at the individual site. That can be rather easy with tools like the SIA, the Swiss guideline, or the VDI guideline, but it has to be done.
Absolutely. Maybe in this context, I would like to ask once again a question, Cornelia and Martin. Could you once again please explain who are the target or the target users of this tool, of this energy? It is not meant to replace engineers and planners? So who should be the user in the end?
Well, it is the idea. There are different kind of stakeholders that we want to address. The first ones are individual families or whatever that are going to build a house, so they can. This is designed. The tool number 2 is designed for them, so they can click on their property and get a first overview about what might be possible. And the other tools, especially the tool number 3, that is intended for municipalities, for energy planning in the cities or in city districts, so that they can have a look and see also what areas are suitable for groundwater heat exchangers, or where they are more suitable for borehole heat exchangers, for example, and also to get an overview about how much energy they can use within the city, because the demand increases from the cities that they have to or they want to provide plans for decarbonization, so energy planning for the future. And for those kind of strategies, they have to know how much energy they can use, and those tools should be helpful for them. And tool number 1 is intended to give a broad overview, more to compare the locations, so that you see, oh, on this site groundwater is available, so it might be interesting to look into those areas. So the tool number 3 about the municipalities will not be publicly available, most likely. So this will really only be for the municipalities. And so also all kinds of private investors or something like this, they can look on tool number 1 on a larger scale to see, okay, we have groundwater here and there are no water protection areas around, so we can go for groundwater systems, for example, in this and that area.
Thank you, Cornelia. So I want to ask one final question before we come to the final statement round to Burkhard. It was very interesting to see this filtering, because it really, this is what is important to look how we as researchers could really provide solutions for a broad population, and don't look at very specific problems which do not affect a lot of citizens. So which kind of conclusions did you draw from when you're filtering, for instance, the thermal conductivity values in the population density, and when you're looking at the thermal conductivity of the piping material? I mean, we don't have so much we can improve, because there's a huge gap between PE and then the next material, which has by multitudes higher thermal conductivity. So are there any technical conclusions you draw from Geocond project?
Yes, indeed. For the first one, the question with the focusing on the population, I think the most clear illustration were the maps from Salzburg that Martin and Cornelia have shown, because there you saw that people are living in the valleys in this place, where there is usually a layer of valley filling, which means lower thermal conductivity than some of the rocks around. And we found the same. A lot of people are not living on top of the mountains, but they are living in sheltered sites, and so there is quite some shift in that. I'd focus more on the issue of the technical outcome of Geocond. Yes, indeed, for the pipe material, there are the metal pipes, which are orders of magnitude higher than plastic. And also they have other problems like corrosion and or a high price if you have corrosion-free materials. The plan or the idea what we wanted to have is a material that is better than PE in thermal conductivity, but like PE in handling and corrosion problems. It should be well like everything else. This is why the Geocond pipes are made from PE as a basic ingredient with these agents that are the ingredients that enhance thermal conductivity. Meanwhile, I found that a group in Canada has done similar things, coming to similar results. So it's possible with that to get up to about 1 watt per meter Kelvin. This is what the material scientists helped us to achieve. Going above that becomes difficult because the pipes start to get rigid and brittle, and though the handling qualities are not good, and it doesn't make much sense to go much higher. And for the grout, as said before, there are very little areas where a grout thermal conductivity above 4 would make a big difference anymore. No, above 3. Sorry, above 3 would make a big difference anymore.
But there are no market-ready products available until now.
Not yet. The Geocond project managed to produce about a total of about 10 tons of grout for these practical tests, and 5 borehole heat exchangers of 100 meter depth. It's possible to do it at that stage. The next discussion is to get, for instance, certification for the pressure resistance of the pipes, because that's a problem, because there are no standard certification procedures outside the PE, PP and such. So it has to be adapted. Also, it's still a cost issue, to be frank. And this is we can reduce the borehole heat exchanger length by about 10% without losing efficiency when using these kind of, or reducing the borehole thermal resistance by 20%. But it's still more expensive than that. And for the grout, yes, it is technically possible to use it, but there is still further work to do to make sure that the quality can be kept up, that the material can be approved, and so on. We made a lot of tests, also freezing thawing cycles and this kind of thing that works fine, but it's still not yet ready on the market.
Yeah.
And the Geocond partners are thinking the project ended now, how on a let's say step or more commercial stage to continue with that.
Thanks for this explanation, Burkhard. So we're coming now to the end of our webinar. Are there any questions I missed? Please, you can use your microphone now in case we missed a question, which would be quite important to be discussed. I see that there was some activity in the chat, so you will get the documentation of the chat, and if you find there any open questions, I would ask all the presenters to provide a short message, and all those of you who are registered to this webinar, you will receive this document in a few days. This webinar will also be recorded, was recorded, sorry, and will be available, that's what I want to say, on the MUSE website, if you want our YouTube channel, if you want to have a look on it again. And I would like to thank you all for your participation, and I would like to invite all the speakers who want to give a final statement for the end of this webinar. Something like, what is your expectation? What are the challenges? Where should we improve mapping in the next years? Maybe I want to ask Burkhard, you would like to give a final statement, a short message from your side?
Well, first I'd like to thank you and all the MUSE and GBA crew for organizing that. It was really very helpful, and I liked also the results from the GBA activities with the G functions. You probably know that I'm a bit familiar with G functions from the past. Anyway, so for the mapping, we already have made a lot of steps compared to about 10 years ago or so. That's a really big increase. And what I can see is that in most areas, for instance, in Germany is not a part of MUSE.
Unfortunately,
we get the structure of the Geological Service for sure. So it is we get information on the ground, and not only on the surface, but also we get more and more access also to borehole, to cross sections of boreholes, geological profiles. So that brings us the third dimension. This is something that's really helpful, and it's openly accessible in most places. It's more and more openly accessible. You do not need to go to the service, to their archives, and so on and so forth. So this is an excellent development, and I hope that to continue as a tool for us. And what we've seen now is to make this tool visible also to non-geologists, and that's fine. So I'm quite happy with what we are seeing.
Thanks a lot, Burkhard. Adela, would you like to give a final concluding statement from your point of view?
As Burkhard said, I want to thank you for the organization of the webinar. And I would include as a further step, it would be important the harmonization of the methodologies to develop the geothermal resource mapping, at least at a European scale. It would be quite helpful, I think.
Necessary, but also challenging, in my point of view.
Yes.
Thank you, Adela. Cornelia, you would give a concluding statement from your point of view.
Yes. So from what we see or what we realized from our project Spatial Energy Planning is that actually we are only at the beginning of resource mapping. Our maps are a great start, but they can be, they should be improved to a higher level because, as I said, they do not include neighboring effects from existing installations. This is especially important for the groundwater heat exchangers, and there are ways to step this up with including numerical models into such a system, and also better models of the demand. But for such a great project, many more resources have to meet. Not only we from the Geological Survey, but then we would also need some more help for the heat pump models to be included, for example, and also the goal of such a big tool would then be a good and efficient management of the underground for the use of shallow geothermal energy. And to achieve this, we would also have to have the support from all the stakeholders that in the end want to use this tool. And this does not only include energy planners, but also the licensing authorities. And we as a Geological Survey and also some other partners that can provide data, for example, all those different organizations should come together, and only then such a larger goal can be achieved. And we are working on this, and I hope that we can get a little bit closer with our project Spatial Energy Planning to this larger goal. And we also hope that we can get other regions in Austria, but maybe from other regions as well, to adapt our workflows and to further improve them.
Thank you very much, Cornelia. Thank you. Very extensive statement, a very important one. Martin? A statement?
Yes, a short statement. Maybe I'm in general happy with the development of the energy system, information system, that also geothermal energies are available, these information systems. And I think it's important to include them in an overall energy planning system like it is in this project. I think it's a good development that you cannot only see the geothermal energy, also you can see other energies you can use on your spot, like wind, solar, or also common heating, Fernwärme, district systems. And yes, I think it's in the right direction.
So, wait a second. Can you hear me now?
Yes.
Oh, sorry, I lost my microphone. Yeah. So thanks all. Sorry for the extra 25 minutes. I think it was worth, and it was very interesting webinar. If you like, visit our events in June, and you will receive the protocol of today, the chat protocol, so you can have a look on the questions and answers again. So thank you very much, and have a nice afternoon, and we stay in contact. Goodbye.
Thank you very much, and goodbye.
Goodbye.
Bye. Bye. Bye.